Thank you all for coming to my talk today. And thank you, Peter, for the great setup. I think that was a fantastic introduction to what you're about to see today. So I think there's a difference between reading about something in the library, reading the Scala doc or poring over the source code, and actually seeing someone use it to build something cool. And today I want to use the ZO library, which is a library for asynchronous and concurrent programming, to build a massively concurrent web crawler that has no races, no deadlocks, follows best practices for thread management and best practices for error management. And I want to do it in somewhere south of 30 minutes. So we'll see how far I get. First, I'm going to dive into a brief introduction to effects, for those of you who haven't seen functional effects, so you won't be totally lost during the live coding session. And then I'm going to dive right in and do a bunch of live coding. And I'll be talking as I go. I don't expect you to understand every single detail, but hopefully the big picture will hold together. And you'll see how you can use functional programming to solve very complex challenges in a quite reasonable way, I hope. So, in the world of procedural programming and object-oriented programming, we utilize, as the basic building blocks, we utilize side-effecting statements. And these side-effecting statements, they're impure, they're non-deterministic, they're often partial, they'll blow up at runtime, and they interact with the real world. They mutate memory, they read from sockets, they write to databases, and so forth. That works all well and good if you're doing procedural programming or object-oriented programming, but when you switch over to doing functional programming, you actually don't use side effects at all. In functional programming, there are no side effects. The only thing that exists in functional programs are functional effects. And functional effects are ordinary values. What they are actually is immutable data structures that describe side effects. And you can think of them as being basically tree-like data structures, and every node in the tree is an operation. For example, it could be, we're going to read something from this file, and we're going to do this database query, then we're going to make this web request API call over here. That immutable tree-like data structure is the functional program. And then at the edge of the world, you have an interpreter, the unsafe run function that Peter talked about, which is responsible for traversing over that immutable data structure and translating every operation that's described by that tree into its real-world side effects. This allows you to program in a purely functional style throughout your entire application, except at the edge of the world. A side effect actually does something. It's like someone going running. But a functional effect only describes the act of going running. It doesn't actually do it. It describes it as a first-class value. It builds that tree, that immutable data structure that describes the effect of going running. And the simplest possible way you can imagine this is with a print line statement. The print line statement in Scala is going to actually print to the console. But you could build the data structure called task here that doesn't actually print to the console, but you can take the print to the console side effect and you can store it inside that data structure. And now you have an immutable value that describes the operation of printing a line of text to the console. That's the difference between a side effect and a functional effect. Doing versus describing. Now, why would you want to program in a functional style? Well, it turns out when you move from doing something to describing it, a whole host of possibilities open up to you. For example, you get the powerful capability that Peter talked about earlier, which is cancellation. You have pervasive, composable cancellation and timeouts across all of your code. It means you can sandbox things. If you want a request to take at most 60 seconds, you can do that. Just time it out after 60 seconds. After 60 seconds, it will be canceled, and all the unnecessary computation will be terminated. That's not possible in the world of imperative effects. You can race a bunch of futures, for example, race 100 futures, and it doesn't matter which one finishes first, the others will continue executing to completion. Why? Because futures don't have the ability to offer cancellation. Same way for running a bunch of futures in parallel. You run a bunch of futures in parallel and you collect the results. What happens if one of those fails? Then all the others continue running to completion, consuming resources. Functional effects, on the other hand, have the ability to terminate unnecessary computation. They're globally efficient, and that gives you global composable timeouts and cancellation. You also have the ability to write effect combinators, that is, functions that take effects and return effects. You don't have that ability with ordinary side effects because side effects are statements, and you can't write a function that takes a bunch of statements and returns a bunch of statements. But you can write a function that takes a functional effect, which is an ordinary value, and returns another functional effect. So you can write timeout combinators, retry combinators. You can take a bit of work and you can replicate that functional effect 100 times in a list to create 100 workers. All the things that you can do with values, you can do with functional effects because functional effects are values. That gives you extraordinary ability to express and factor out duplication inside your program structure. You have resource safety. So you have that in ordinary Scala with try finally. You don't have it in future though. You do have it with the functional effect system. The functional effect systems give you a version of try finally that can work across asynchronous boundaries in your code, work across concurrent regions, work across synchronous sections of your code. They give you very powerful capabilities to guarantee that you don't leak resources. We have fiber-based concurrency models that Peter talked about, which give you the ability to spin up hundreds of thousands, maybe even millions of fibers which don't block, which perform very efficiently, which have growable, shrinkable stacks, and which can even be garbage collected, which are killer benefits that have real practical benefits for today's business applications. Of course, you get equational reasoning and type-based reasoning out of this because it is FP. And what that means is practical benefits for you as a programmer mean you can refactor your functional code without changing its meaning. That's not true with statements. That is always true with functional effects. You can inline functional effects, you can factor them out into variables, you can introduce functions, eliminate functions, you can do all of that, and the meaning of your program is guaranteed to remain unchanged, which gives you the ability to go into code and just clean it up without thinking about it. You have to be very, very careful when you're refactoring side-effecting code. Error management. Today's functional effect systems have very powerful capabilities to manage errors. So they can propagate errors across different subsystems, asynchronous subsystems, concurrent subsystems, and so forth. And finally, they give you an unprecedented ability to test your code because functional code made of pure functions, which are deterministic and total and free of side effects, are much, much easier to test than impure functions that return something different every time and that sometimes throw exceptions and are doing lots of things on the side effects. So these are the practical benefits that using a functional effect system has for you as a programmer and for the business application that you're writing. Zio is a functional effect system that I work on, and the core data type in Zio is called Zio. And what it is it's a functional effect. It is a description of interaction with the external world. It could be concurrent or asynchronous, or it could be synchronous, or it could be resource related or environmental related, but it is some sort of description with the external world. The Zio effect type has 3 type parameters, R, E, and A. R represents the type of environment required by the effect. So effects can require a certain type of environment. That environment can give them capabilities. For example, interacting with the console, or interacting with a database, or so on and so forth. The E-type parameter represents the error type of the effect with which it may fail. So different effects may fail in different ways with different types of errors. And finally, the A-type represents the success type of the effect. If the effect succeeds, then it produces a value of that type. And a good mental model you can use for the Zio effect type is as a sort of purely functional version of the following function from R to either E or A. So you can think of a Zio effect as a function that needs an R. If you want to run that functional effect, you need to give it an R. You need to give it the environment that it requires. And then you're either going to get back an E on the one hand if it failed with some error type, or you'll get back an A on the other hand if it succeeded with the value. Now, you don't always need all of these different type parameters, so there are some type aliases and companion objects in Zio to remove the ones that you don't need right now. All of these are just type aliases. There's only one effect type in Zio. However, these type aliases are common enough that it's useful to bake them into core. The type UIO represents an effect that requires no environments at all, and that's modeled with the any type parameter. So any means it has no requirements at all. You could give it an int, you could give it a string, you could give it a database. It doesn't care because it's not going to use it. It cannot fail with any error. You know that because the e-type parameter is set to nothing. And in Scala, there are no values of type nothing, which means there's no way you can fail with a value of type nothing because you can't construct such a value. And finally, UIO succeeds with a value of type A. So UIO is an unfailing or unexceptional effect type that can only succeed with a value of type A and doesn't require anything. Task, on the other hand, doesn't need anything but can fail with any throwable or succeed with an A. This is the direct analog of task in Monix. Task R is very similar to task, except it does require an R. It requires something from its environment, maybe some configuration, maybe access to a database or a console or a web API or something like that. And then finally, IO represents an effect that has no requirements from its environment, but may fail with an E or may succeed with an A. With procedural side effects, we construct programs using statements. And with functional effects, we construct them generally using for comprehensions, which you've probably used before with future, which are basically a series of flatMap operations followed by a final map. The syntax looks a little bit different, but you can see the parallel here. Both of them are sequential, and in both of them, subsequent operations can depend on the results produced by preceding operations. So here's the exact same program written in a procedural style and written in a functional style. And I will admit, using for comprehensions, it takes some work. You have to learn that. That's a learned skill. But you can learn it, and it doesn't take too long. And once you do learn it, the entire world of functional effect systems is open to you. All right, so with that background, whirlwind tour of functional effects, we're going to dive into live coding. And I'm going to be using Metals for this live demonstration. Metals version 0.5.1.2. And I'm using Metals because I absolutely love it. It is an amazing tool for developing with Scala. By far my favorite tool, and you're going to see, I think, some of the cool features. It's going to do autocomplete and all kinds of other cool stuff during this demo. The setup of this problem is as follows. So we are going to build a web crawler, and we're going to do it in a generic fashion. So what we want to be able to do is write the core engine that does the web crawling, and then other people in our company are going to plug in their own processors into our web crawler. And some of those page processors might rip out keywords and build inverted indexes and do other sorts of things. Others might extract structured data. Who knows exactly what people will plug into it, but we're building the infrastructure layer that other people in our company can leverage in order to crawl some website or set of websites. And here's what we have access to. We have access to this get URL implementation function, which is just calling something baked into the Scala standard library. So this is scala.io.source.fromURL that's capable of grabbing a URL, the content on a URL, and converting it into a stream, which is then converted into a string. This is not the best way to solve this problem. You should not use this in production code, but it's going to get the job done for today. And we have this crawl state data structure, which is going to hold the state of a crawling operation at the current moment in time by collecting all the URLs that we have visited so far to make sure we don't accidentally traverse the same URL more than once. And also it's going to collect a list of errors which may have been produced as we're processing the different web pages during this crawl operation. So that's going to be our state. It's going to collect those two things. And then finally, what we're going to do is we're going to be implementing this crawl function, which is responsible for executing the crawl. And the arguments that you provide this crawl function are as follows. First off, you have to provide it a set of seed URLs. So this is how you seed the web crawler. It's going to jump onto these URLs, it's going to pull back their content, and it's going to traverse them recursively until it's done with the crawling operation. You also have to provide it a router. And the router is basically a hook that allows you to plug something in to the web crawler that can terminate the process. What the router is it maps a URL into a set of URLs, which could also be an empty set. So your router, if it decides it wants to stop crawling, if, for example, you've left a subdomain and now you've hopped over to some other website that you don't want to crawl, you can return an empty set, and that's going to end up terminating the crawl process. And you can also use the router to do remapping. So if you want to map one URL into several TLDs, top-level domains, or something like that, you can use the router to perform that type of remapping operation as you're crawling. And then finally, the most important function that you provide, the crawl function, is the page processor. This is where you do the heavy lifting. If you're building an inverted index, or if you're extracting structured data, or if you're counting keywords, or whatever it is you're doing, the meat of your processing of this set of URLs is contained inside this processor function, which is fed the URL and the content of the web page. And it gets to return an effect here, a functional effect, which might fail for some error E, but which produces no information. So this is your page processor. You can do whatever you want in here. And you can also fail with an arbitrary error type E. And our crawl function here is going to return a functional effect that uses a blocking interface. So this blocking interface, I'll explain this here in a second, it's going to give us the ability to shift a computation to a blocking thread pool. Just like when you're using Future, for example, you always want to designate operations, I/O operations that are blocking. When using a functional effect system, it's best practice to make sure that you execute all blocking I/O operations on a separate blocking thread pool. You don't have to create that, you don't have to manage that. Zio provides a one-liner that allows you to simply denote this effect as being blocking, and it will go ahead and manage that for you. The effect does not fail. That means the act of crawling this set of URLs cannot fail. That's a design choice. It's a good design choice, I think, in this case, because it will turn out that as you try to crawl a bunch of URLs, many of them will not exist, or the servers will be down. That should not kill your overall crawling process. At best, you should collect and aggregate those errors. At worst, you can ignore them. But what we're saying here is the act of crawling, based on this set of initial URLs, is never going to fail. And then finally, what this is going to produce, in addition to invoking our page processor on everything that's crawled, what this is going to produce, the success value of this effect, will be a list of errors produced by the page processor, which of course might be empty if the page processor never failed. And then in addition, presumably our page processor that we're feeding the crawl function is doing something useful on the side, like building that inverted index or extracting the structured data or whatever it is that it's doing. All right, so inside this function, I've created a little loop helper function. And the reason for this is we're going to need to do iteration. And of course, in a functional program, we iterate by recursing. So we're going to involve recursion here. And we don't need to pass the same arguments again and again and again. So I just created a little helper that's going to enable us to iterate and explore this set of URLs progressively as we expand outwards and crawl everything we're supposed to. We're going to start, however, with this getURL function. So this is from Scala. This right here, this getURL implementation function, is straight from Scala. And this is side-effecting code. This is not easy to test. It's partial. It could blow up for any error reason. And of course, it's impurely going to interact with the external world. You can take code like this and you can pull it up into a functional effect system. In fact, it's very easy. Functional effect systems make it very easy to do that. They're one-liners. So what we're going to do is we're going to take this side-effecting code and we're going to lift it up into a purely functional Zio effect. Now there's a few different ways you can do that. You can call the effect method, which is for synchronous effects, the effect async method, which is for asynchronous effects, or the effect blocking method, which is for blocking synchronous effects. So we're going to do that now. We're going to call effect blocking, and we're going to specify get URL impl, and we're going to feed it the URL. And we've got an error here, and the error is caused by the fact that when we import this blocking side-effecting code into a Zio effect, the Zio effect fails with type throwable. That's because who knows what's happening in that side-effecting code. It could fail for any reason at all. Whereas the type that I gave this is exception. The failure type I gave getURL is exception. So what's happening here is we're getting a type error because the error type from effect blocking is too broad. And what we have to do here is we have to decide how to handle anything that's not an exception. And the way I'm going to choose to handle things which are not exceptions is I'm basically going to kill the fiber that's running this. So if we get back some sort of fatal error, it's not an exception, then I'm just going to kill the fiber. And there's a method that you can use to do that called refine or die. And what you provide refine or die is a partial function that allows you to pick out the classes of errors that you wish to handle. So right now I'm picking out all exceptions and I'm saying, yes, I'm going to go ahead and reflect those in the return type of this Zio effect, but on any other throwable type, I'm going to go ahead and die. I'm going to kill the fiber. This is a fatal error. This will terminate the fiber if anything else happens. And in general, that's the thing that you want to do. You don't want to be able to catch all errors. You only want to be able to catch the subset of errors which are recoverable. For example, you would never want to catch Stack Overflow error or out of memory exception or lots of other, basically anything that extends error in Java should never be caught. So now I've taken this side-effecting code and I've lifted it up into a pure effect and I've refined its error type to be the subset of error types that I have defined to be recoverable. So if it has an exception, it's recoverable, and otherwise I'm going to ignore it and it's going to terminate the whole web crawling process. And note here that Zio will take this effectful code, and when it comes time to execute it at the edge of the world, it will shift it onto a blocking thread pool, and it will execute it there safely in an unbounded, infinitely growable blocking thread pool. And then after it's done executing that code, it'll shift the computation back to where it's supposed to be running, which is the main Zio thread pool. All right, so getURL is done. Now I'm going to have to use this crawl state data structure at some point. The crawl state contains this list of visited URLs, the URLs I've already seen, and then this list of errors produced by the page processor. It has two helper methods here, visitAll, which just adds this set of URLs to those already visited, and then this logerr function, which just adds an error into the set of errors that are logged with this crawl state data structure. So I'm going to have to use this here in a second. All right, loop. I'm going to try to implement this function here now. And I can see at a high level that what I need to do is I need to iterate over seeds. I need to go through each of these seed URLs, and I need to pull back their content. I need to call that getURL function that I just wrote and pull back their HTML content. And then with that HTML content and the URL, I can feed that into the page processor, which can do whatever it's going to do and maybe fail. And then I can take that content and I can scrape it for more URLs. And after I scrape it for more URLs, I can add those into a set and I can just keep on recursing on that set of new URLs and continue the process recursively. And somewhere in there I need to go ahead and call the router so it has a chance to look at these URLs that I'm scraping, and it can decide whether or not to continue the process or stop the process. So the first thing I'm going to do is iterate over this set of URLs, and I want to iterate over it in an effectful fashion. I want an effectful for loop. And of course, there's something in functional programming that can do this, and it's known as traverse. Traverse is an effectful for loop. And in Zio, it's called for each. And you provide it the thing that you want to iterate over. This is the thing that you're for eaching over. And then you provided a closure that will be passed every single thing inside that list or set or whatever it is. And then inside the body here, you get to return a functional effect. And so my functional effect will be placed inside this for loop. And then what for each returns, it's like a really super powerful for loop, because what it's going to do is it's going to for each over everything in that set. It's going to run the closure on every one of those things, and every one of those things will return something in an effect. The for each is going to collect them all together back in a list. So if you imagine like a for loop in an imperative programming language doing the same thing it does, but like collecting the results of each iteration in the body, you'll have some sense of what for each does in Zio. All right, so I have this seed here, this URL, and one of the first things I know I need to do is I need to retrieve its content. So I'm going to go ahead and do that now. Now instead of a statement, I'm in a for comprehension, so I'm going to use the backward arrow syntax. I'm going to call getURL on this seed, and that gives me the HTML content. And then now I need to scrape that content for new URLs. Unfortunately, I already have a helper function to do this. I didn't want to code this here. So I have this helper function that's going to scrape this HTML page for URLs by using a regex. Again, not recommended practice to do this in production. You can see just nasty little regex here that pulls out all the A tags. It gets the job done. All right, so I'm going to call scraped here, and notice I'm going to use an equal sign. This is a little known feature of Scala for comprehensions, where you can introduce a variable inside a for comprehension by using an equal sign. This will not translate into a flatMap. It will actually translate into a local val inside one of the blocks passed to the flatMap function. So scraped is going to be equal to extract URLs on this particular seed and this particular HTML content. And this gives me a list, which I need to convert to a set, because I don't care about duplicates. If, for purposes of crawling this set of URLs, if I get two URLs that are the same, I'm just going to collapse that into one because I only want to crawl it once. And so I convert it to a set here. And then I'm going to pass it to the router. So this router here is going to look at each URL, and it's going to decide whether to return an empty set to terminate the process because it doesn't want to explore that URL, or maybe it will rewrite it to a bunch of other URLs. All right, now I've scraped this. Now what do I need to do? Well, I need to somehow keep track of the fact that I'm going to visit these URLs. And I also need to invoke the page processor on this URL. So let me do that first. Let me invoke the page processor. So this processor here is going to return unit. So instead of giving unit a name, I'm going to use the underscore in the for comprehension. And I'm going to call processor on the seed URL and the HTML content. And the processor, it now has its URL, and it also has it has the URL, and it also has the content of the web page, so it's free to do whatever it wants. And it is going to return something of type IOE unit. So that's an effect that might fail. So I have to deal with that possibility. So what I'm going to do here is, this gives me an IO of E unit. I'm going to call .either on this, which is going to give me an effect that returns an either of E unit. So it converts the effect which might fail into one that doesn't fail, and gives me back an either of E, or the success value, which in this case is unit. So now I have this either here, which is useful. It's not enough. Okay, so now I've retrieved the content of the web page. I've scraped it for new URLs. I've called the page processor, and if the page processor failed, I've converted that to a value, to an either. So now I have an either which contains that error. And now what I need to do is I need to keep track of the error, if there was an error, and also the fact that I'm going to be visiting a new set of URLs. The ones that I just scraped, I'm about to visit them in a recursive fashion, so I need to keep track of the fact that I'm going to visit them by updating a crawl state data structure. This crawl state contains this set of URLs and this list of errors produced by the crawling process. Fortunately, when I sketched out this loop function, I provided it a ref, which can be thought of as a purely functional var. It's basically a purely functional var with atomic operations. So it can be accessed from lots of different fibers, and they won't clobber each other when they use ref. So it's concurrent safe, unlike var. And this ref here contains a crawl state of E. So it's passed into the loop function, so all I have to do is modify that ref and add the new set of scraped URLs, as well as if the page processor failed, then I'm going to have to take that error and I'm going to have to stuff that into the crawl state to keep track of it. So in the next line in my for comprehension, I'm going to try to do both those things. And I'm also going to try to extract out, I'm going to produce the set of URLs, the new URLs, that I want to continue the iteration process with. This is not the same as the set of URLs that have been scraped from the page. And the reason for that is I may have already visited some of these URLs before. And so what I really want to do is I want to take the set that I scraped and I want to subtract away all the ones I've already visited to make sure that I don't visit the same web page more than once. So let's see if I can do all that in a single line of code. I'm going to call a function on ref called modify. And modify allows me to do two things at once. First off, I can update the value of the ref. This ref holds a crawl state. So I can change it to a new crawl state. But also I can return a piece of that crawl state. Modify allows you to do both those things. And you do that by returning a tuple. And the first element in the tuple is whatever you get out of modify. It's whatever you want to return from the modify operation. The second element in the tuple is the new, in this case, crawl state that will be used to update the value of the ref. So here I have my crawl state, and what I'm going to do is, in the first element of the tuple, I'm going to compute whatever I want to get out of the modify operation. So what I want to get out is scraped minus minus state dot visited. So I'm going to take the scraped URLs, and using set difference, I'm going to subtract all the URLs that I've already crawled. And that way I'm getting a brand new set of URLs that I've never ever seen before. And then in the second element of this tuple, I have to return the new crawl state. And the new crawl state is going to be as follows. It's going to be state.visitAll scraped. So we're adding in all the new scraped URLs into the crawl state. And then we also have to deal with this error. So how we'll deal with this error is as follows. Unfortunately, I'm going to have to introduce a block here. Well, I don't have to, but it'll prove to be easier. So this is the new state. I need to return the new state out of here. What I'm going to do is I'm going to take this either, and either it's an error if the processor failed, or it's unit if it succeeded. So what I'm going to do is I'm going to fold over this, and if I got an error, then I'm going to call S2 log error. And then if it's a success, then I need to just return S2. Right, I need to ignore the unit. Okay. So now I've taken this state, I've added to it all the ones that I scraped. So I've added all the new URLs that I've scraped. And then if this either had an error in it, then I've added that error into the crawl state. Otherwise, I've just used the same crawl state. Does that make sense? All right, so at this point, I've called ref modify. So I've modified the value of that reference. And remember, ref is concurrent safe. That will be important later. Ref is concurrent safe. So I've produced a new ref that has added in all my scraped URLs and has added the error if there was an error. And simultaneously, I've produced the set of new URLs by taking the scraped URLs and subtracting all the URLs that I visited at this point in time to produce just the ones that I haven't yet traversed. And that's what I get back from the modify operation here called new URLs. So now I'm going to yield that out of the for comprehension. And then out of this for each, I'm going to get back a list. Actually, I'm going to get back an effect that succeeds with a list of a set of URLs. The set of URLs comes from here. The list comes from the fact that I'm for eaching over a collection. That's why I have a list of a set of URLs. And the fact that it's an effect, of course, is a consequence of the fact that we're using a functional effect system here. So this is a complicated structure. I want to simplify it. And in order to simplify it, what I'm going to do is I'm going to map over this effect. I'm going to map over the success value of this effect. And what's inside this effect is a list of a set. So I'm going to take this list of a set, I'm going to convert the list into a set, and then I'm going to flatten that out. And then at this point, I'm just going to have an effect of a set of URLs. An effect of a set of URLs. And given that effect of a set of URLs, I can flat map over that effect using my new URLs, and I can call loop recursively on it. So I'm going to feed this new URLs into loop. I'm going to call this recursively. And I'm just going to pass along the ref here on modify. All right, so I tried to compile this. I saved this. And Metals is giving me back this great error message saying something's wrong here. It's saying I found a ZIO effect. And if you look at these two effects, they're exactly the same. They both require blocking. And they both produce unit. The only thing that's different is the error type. We're getting an error message because it found something that could fail with an exception, but it expected something that couldn't fail at all. In other words, we are using the Scala compiler here to force us to deal with errors where we should deal with them. This is the benefit of typed errors. Here, we know for a fact the Scala compiler is not letting us get away with something. We've said this loop function cannot fail, but yet somewhere in here, there is the possibility of failure. And if you look carefully, you'll find it's coming from get URL. It's coming from get URL. Because get URL can fail, this entire for comprehension can fail. This effect produced by this for comprehension can fail. And so we're getting at compile time feedback that, hey, we said we wanted to make this part of the code infallible, and we haven't done that, so let's go ahead and fix that. And one of the easiest ways we can do that is just to wrap this for comprehension in parentheses, and we'll provide a fallback in case this whole for comprehension fails. So what does this produce? It produces a set. So we'll just produce an empty set of URLs if for some reason retrieving the content of this particular web page failed. So if we can't pull back the content of web page because the URL's malformed or the server's down or whatever, we'll just produce an empty set of URLs out of that. And now we have compile time proof that we've handled our errors in accordance with our specification as encoded by our type. And now we're almost done. We just need to call this loop function. So here's what we're going to do. In a final for comprehension, we're going to create a ref, and you do that using ref make. And we need a crawl state here that contains a set of URLs. We're going to start it with a set of seeds here that were passed in. And then a set of errors, or a list of errors, we'll do list empty e because we're going to not have any errors to start with. And then we're going to call loop here on the set of seeds and the ref. And then finally, we're going to pull out the state from the ref. After we're done looping, we're going to pull out the state from the ref. And then we're going to yield here state the errors, because that's what we're supposed to do. And it's compiling. However, there's one thing we forgot. Currently, this code is entirely sequential. There's no concurrency. However, we were smart enough to use a concurrent safe structure here called ref. It means we can take this purely sequential version and we can turn it into a parallel version by changing this for each into for each par. And now it's massively parallel. In fact, it's too parallel. Because if you crawl 1,000 links on a web page, well, you're going to have 1,000 concurrent connection requests all trying to pull down content, which is going to saturate your local bandwidth and probably not be all that ideal. So instead of for each par, we're going to use a variant called for each par n, and we're going to limit concurrency to 100. So we'll use 100 fibers at a time. So this will be a 100-way concurrency. And it shows you a bit of the power of programming with a functional effect system. Because we don't need to worry about locks, we don't need to worry about race conditions, we don't need to worry about threads or thread management, we don't even need to explicitly use any thread pools. We can just use high-level operations like blocking to shift computations to where they're supposed to run and back and have Zio manage that for us. And we were able to take a sequential version and by changing 3 characters, turn it into a massively parallel version. This gives you a taste for the power of functional effects. And this is just a small taste, I think. If you dig into libraries like Zio, you're going to find features like software transactional memory. And you're going to find a whole host of, like, you can zip 2 effects together, or you can call zip par to zip 2 things together in parallel. Or you can call collect all to gather a bunch of results from many different effects, or collect all par to do a bunch of things in parallel. Parallelism and concurrency, error management, error propagation, best practices for thread management, all these things come for free, as well as pervasive composable cancellation, interruption, and timeouts. This is truly, in my opinion, it's one of the work in Monix and Zio and Cat's Effect and all the stuff that's happening out there. FS2 is some of the most exciting things to be happening in the Scala ecosystem for some time. And I think that's why the functional programming community is really growing right now in Scala. It's because the community is building great software that solves real problems. And before I wrap up, I'll just do one more review of this, just to give you a sense for the big picture, and then we'll call it a day. So this crawl function here, it takes the initial list of seeds, the router, and the page processor. It returns an effect that uses a blocking interface. And by the way, Zio is fully inferable. So you can delete any type signature anywhere, and it can be inferred by the Scala compiler, which also means you can use IntelliJ IDEA to auto-insert type signatures if you want. And then What it does is it defines a helper loop function here. Why a helper function? Because you use recursion if you want to do iteration in a functional program. And then it uses this for each construct, which started out as for each but ended up as for each par n, to iterate over all these seeds in parallel up to the specified level of concurrency. And for every seed, it's going to execute this. And what does this do? Well, it gets the content of the current URL. It scrapes that content for new URLs and sends it through the router, which can determine whether or not to proceed or not. And then it feeds it all to the page processor, and the page processor can fail. So if we didn't call this either here, we'd get another type error. Basically, the compiler's helping you do the right thing. You don't have to worry as much about error management. When you're using typed errors, the compiler just guides you to do the right thing. And so we called either to convert that into a value. And then we modified this ref here, which is a concurrent safe structure. And we added, first we computed the set of URLs that we haven't visited yet by subtracting from the scraped ones, all the ones we've seen to date. And then we added the new URLs as well as added the error if there was one. And I did this in a compact fashion, but if you like pattern matching over either, you could do it that way too. I just wanted to fit it on one line. And then this for comprehension can fail. We know that. The compiler told us that it can fail. And it forced us to deal with this error. How did we deal with the error? Well, we said, if the get URL fails, we're just going to have a fallback here. And our fallback will succeed with the empty set. So we produced an effect that succeeds with the empty set. And thus, we get the compile time guarantee that the body of our effectful parallel for loop is not going to fail. And then we took this, we got a list of a set out of here, and we flattened that out to be just an ordinary set of URLs. And then we called flatMap on that effect to loop, continue the looping process with the new URLs that we got out of there. And then finally, we had to do a little bit of setup. We had to make a reference that contained the initial list of seeds and an empty list of errors. We had to get this whole process starting by calling loop, and then we were able to extract out the state and pull out whatever errors we ran into as we were doing the web crawling process. So all this code is on GitHub. Let me show you where it is. So if you want to do this exercise yourself, you can just hop over to this URL here, pull that out, and then the scaffolding is all in place, so it's a good exercise to get a feel for just how powerful these functional effect systems can be. I hope you've enjoyed this live coding, and I'm sorry I ran a little bit over time, but almost managed to fit it in, and I believe lunch is out there waiting, so thank you all for coming to my talk.
It's lunchtime, and we'll be back at 12:30 with both a talk and a workshop.